Well, we'll start out. I've got two antennas here, and I got a blank space between the two. The signal is going from one to the other, so that makes the universe the transmission line. How many people know what the impedance of that transmission line is?
377.
Two guys know who Maxwell is. Yes. So the universe has an impedance of 377 ohms. So you can think of your antenna as a 50 to 377 ohm impedance transformer, not 50 to 50. Okay. Ta-da, 377. Okay. We're going to talk about some of the finer points of optimizing a dish antenna for best performance. Next. This is an infrared photo of my dish that I use for 10 gig moon bounce, run about 5 megawatts ERP when we're talking to friends in Europe by using the moon as a satellite. We think of it as the communication satellite God put in orbit. The batteries have been dead for a while, but some of us use it anyway. What I'm trying to point out here is we have to start thinking of 1420 not as a radio wave, but as a long wavelength infrared radiation. This is a bizarre concept. I can take a 50 ohm resistor, put a voltmeter across it, and read an AC voltage. There is microwave energy coming out of that resistor. The second law of thermodynamics is doing just fine. It's basically converting part of the electromagnetic spectrum down to a lower frequency part. But the vibrating atoms and everything together are making noise. Here, we have a dish sitting out in the open. As you can see, the dirt is hot. The dirt is radiating microwave radiation. If we look at the dish, the bottom curvature of the dish is reflecting the cold sky. The top part of the dish is reflecting the noise from the dirt. So number one is we don't want our antenna system looking at dirt whenever possible. And I never realized that the paint that they put on that zigzag for Andrews created an issue. That may get scraped off soon. Next. This is a good old formula for finding the focus of a dish. Next. You take the diameter followed by the depth. And the two should have been over there, and it looked fine on the first artwork, but didn't make it in PowerPoint. This is the formula. I've seen this calculated out. I've literally had hundreds of dishes on the antenna range. I'll take the whole antenna range to conferences and so forth, set it up. It's kind of interesting what some of the guys show up with. But it's amazing how this can be confused. Next. Here we have the edge of a dish, and as you can see, the edge is rolled. This makes the dish stiffer, almost a bit structurally. If you walk into it, you're less likely to need stitches afterwards. But the headache is the guys will measure the whole dish. You have to measure where the parabola surface changes being a parabola. So you don't measure it to here, you measure it to here. Let's see. I bring. Nope, it's still in the front seat. Okay, next. Here, if we take just some basic math, look, how come we chopped off the bottom?
I've never figured this out. How do you get this to go away?
Modern technology. If builders built buildings the way programmers write programs, one woodpecker.
Careful, we got a programmer in here. We gotta be careful.
I understand most of all.
I cannot get that to go away.
Oh, well, I was just showing how to go through the calculations and find the feed point. Okay, next. Okay. Here we have everything coming down. We've calculated where the feed point should be. Next. Here's where most of the guys go wrong. This has focused to an infinitesimal point. Here's a time-honored tradition. This is not an infinitesimal point. If you put your feed there, it's just not going to work right. And you're on a wavelength where the waves are roughly about 8 inches long. You are not going to get an 8-inch wave into an infinitesimal point. So finding exactly where the focus point is, people tend to put their feed right there at the edge. Virtually every dish I've ever tested, next, works better when you bring it inside. So once you calculate you've got your feed, you're going to want it closer to the dish. How much closer is, there's no really good way of predicting it without knowing an awful lot more about the feed than is usually available. Probably one of the best things you guys could do would be to focus on sun noise, which is a nice far field, move it in and out, and you'll find that it works better or slightly closer to the dish than at the feed point. Next. Another headache that we've seen, and the satellite guys actually ended up with regulations requiring this. When I have my feed, the very center of the dish is a reflection point back to the feed. Virtually every high gain amplifier has noise coming out the input. If you got a network analyzer, this means your S11 is a positive number. And it's amazing how many low noise amplifiers will show that. So you not only have the problem of feedback to the amp, the preamp looks hot. So you're adding to your own noise. Now, a lot of amplifiers will oscillate. Back in the days of before we had DirecTV and we all had our C-band dishes in the backyard, they actually required an isolator to be built into every LNA. Because if I've got 10,000 dishes all looking at the Galaxy 4 transponders and a few percentage of them are oscillating, I can take out satellite.
What's an isolator?
Isolator is the RF equivalent of a check valve. The signal goes this way, it doesn't come back. So you put that on your preamp and anything generated stays inside the preamp. So what do you do about this? You put some type of structure down there that disperses it. I once went down to an automotive store and got a metal funnel for putting gasoline in the lawnmower, and I had a metal funnel down here. It doesn't need to be that extreme in the angle, but just something with almost like a domed hubcap. Put it down there, disperse that up, and you'll get a little bit better noise temperature on your system. Well, we're working with radio waves that are between 7 and 8 inches. So it's going to need to be at least that big. In fact, you've got a limit on the size of the dish. The dish needs to be 10 wavelengths across to bring the signal to a focus. At this frequency, that works out to about 6 feet. Anything smaller is acting a lot. You can make 5 wavelengths kind of work. Anything smaller than that just turns out to be a plane reflector. The Stanford dish, the supports is something that's totally misunderstood. If I'm looking at a scene and I put a big plexiglass rod in front of me, it distorts that scene. But it's transparent. Yeah, but it distorts the scene. If I make my supports out of wood, fiberglass, some plastic, it's still distorting the signal that's coming through them. Metal is worse. Using wood or very thin plastics a little bit better. But 2 problems are happening. One, because the feed is in the middle, it's creating a V-shaped shadow in the dish. In this case, their feeds supports are probably blocking 10% of the dish because of the 3 V's that's being formed by it. If I can move the support from the middle of the dish out to the edge, I get rid of most of that V. So your feeds really shouldn't be coming to the middle, they should be coming to the edge of the dish. In this case, you can see they had some structural issues. The edges wouldn't have supported that. They decided to make the dish bigger. But mechanically, it's best if you can take them all the way to the edge rather than the middle. Okay. How did you guys watch the eclipse? I tried various filters in front of my infrared camera and they did not pass infrared with a flip. So that's actually a reflection image off of the tinted windshield of my car. You can see the windshield wiper down there. Okay. Now, I have a prototype that I haven't finished yet that I'll be writing up. I didn't get it in time for the proceedings, but I have a website where I have a lot of antenna projects. So I have a feed rather similar to this one.
Open from the computer too, so the camera will get out.
There you go. All right, that's good.
Okay. A feed similar to this, which is made for 1420. You can hook it up for both vertical and horizontal polarizations at the same time, or left and right circular polarizations at the same time. Because it's got two feeds. I plan to get this thing finished up and it will be available on my website here quite shortly.
Computer again.
A little more practical than this one. But it is well tuned.
So that's the entire pickup right there.
Yep.
Is it,
The patch will be slightly larger.
He's got the SMA connector coming here, grounded on the back plane. Comes through, soldered up to this copper plate, got some fiber insulation board.
do you need to have that full copper plate? Or
No, it doesn't have to be that big. It was just what was available when I was playing with it. Yeah, and this particular one is, you've got two feed points. And then if I trim the edges of the patch, I can make those left and right circular. And is there any frequency other than 1420 you guys are playing?
1620, 1627,
What's that?
1630,
What's there?
485.
8 megahertz, just background with Galaxy.
Okay,
And 6 gig.
okay. What's it, the other frequency, you said 1620?
No, 608.
608, okay, 6 gig, okay. I've got feeds for that. Also got very broadband feeds. But
how broad that is?
I sell some Vivaldi antennas that are 1.5 to 15 gig.
We saw Vivaldi horn this morning. We had a Vivaldi section.
Mhm.
1 to 8.
Yeah,
a couple of them.
I call a Vivaldi antenna a ridged horn without the horn.
Yeah. 1 to 18 or something like that. That's what they had it on there.
I've got some similar with a solid black on the outside.
No,
No,
Is
these
it-
were some other.
it had like a translucent
Okay,
something or other.
okay. I have
Big aluminum ribs. down
I
there.
have several similar versions I use on the antenna range quite often.
And so that feed that you have there, the patch feed, you could actually use that in front of your dish.
Yes.
Yes, right, as your pickup.
And as I said, you could be linear polarization or circular polarization. And I'll try and have it finished up and put on my website here in the next couple of weeks.
And will it, and what about the gain or the sensitivity of that, do you think?
Should be fine.
You don't have any relative number, so like compared to any other standard antenna that you happen to have, or?
Tell me an awful lot about your dish and I'll give you a better answer.
I see, okay.
What is the F over D to your dish? How many wavelengths is it? What is it made out of? And made out of is somewhat interesting. You all remember Voyager going to the outer planets? That was a 10-foot carbon fiber dish. They took the carbon fiber dish out on the antenna range, tested it, it met specs. As a weight savings, it was never metallized. So those photos came back from the outer planets on a carbon surface dish. Tell me again that carbon fiber is used to make stealth aircraft because of its low radar.
I think it's because it reflects it.
No, for strength to weight ratio. So the carbon fiber looks just like sheet aluminum once you get above about a gig.
That illuminated data. Does it have a specific application range for the airport?
That's changed partially by the size of the ground plane,
You can tune it to the shape of your.
somewhat. It doesn't work if you've got something with an F/D of like 0.6. But if you're the usual 0.35 or so, it should work fine.
The other question is,
From Germany?
no, social.
Pretty close. I'll be in Zurich next month. You have the weirdest airport on levels. I didn't take the train up to Ramshorn and then to the big flea market at Friedrichshafen.
Oh, okay. That's good. The question is, you can see in this environment, the radio astronomy, a lot of anyone can have what I like to call a mini skirts around.
Come up to the
Or-
front so we can
Yeah,
hear,
can you-
okay?
You gotta get closer to the microphone.
The question is, I've seen frequently that there is an improvement to reduce the noise, the overall noise of the system. They put a sort of a net around, I call it the mini skirt. It's a circle around the,
Go back to my number one.
is it something that would,
That, yeah, right there. Okay. It,
it would be I would call it a conical shape of a net that goes around the net.
that's so the dish doesn't see the dirt.
Yeah,
Okay.
doesn't see
Is
the
it,
back.
is there a rule or some sort of guideline on how to put that, add on metal to your existing antenna?
You can either make the dish effectively bigger by adding the screen around the edge. And it doesn't have to focus it, it just has to block it off. Or make the whole ground around the dish a lot of chicken wire.
But the surrounding things like the professional do would help, just,
Oh, slightly, yes. Because you're gonna have this looking up. And you're trying to, your feed is, you always have a trade-off. I've got a feed here looking at this. I want to have the feed go near the end of the dish, so I can use the whole of the surface of the dish. But then some of the energy misses it. And you don't want that miss seeing dirt.
so it is an add-on which you would recommend to add to improve the noise.
Bigger is always better.
No
You've
replace-
seen a lot of the dishes, you'll see them later come back and that have a chicken wire going out an extra 3 meters or so, making the dish bigger. And part of that is to cut down what the feed is seeing in noise off the edges of the dish.
Yeah, I use a grid antenna and I have wire screening out and it's just to prevent ground noise from reflecting back into.
Yeah, now you see a lot of stuff on satellite communications mentioning gain over temperature. And I'm kind of wondering if instead of gain over temperature, we should be using the gain over computer background noise. Because that's always a lot more.
Oh,
than
but
the
you put
ground.
one little ferrite bead on your computer and all the noise just goes away.
Horse numbers.
Well, I have a problem. We were trying to build television antennas into laptop computers.
Oh,
And this was so they could, this is back in the day when we were gonna have digital TV coming on. They wanted to have the laptop computers do digital TV. And we built some very broadband antennas that went in there. The problem was the memory. You've got those refresh rates, and the vast majority of the noise was coming out of that. And couldn't receive it.
Yeah.
Well, I don't understand the problem. These pass FCC. Well, the FCC regulations say that this computer will not unduly interfere with a television 3 meters away. But when they are rather intimately located, didn't work.
Okay, I have a question.
He's got one.
Okay, go ahead.
So these skirts that he's talking about, that come up on the end of those,
Mhm.
so first off, you do recommend putting them on, right? Is that what you're saying?
Or get a bigger dish.
Well, I mean, if you're stuck.
Oh, I love chalkboards.
So you're stuck with the digit now, so I'm gonna make it better.
So here's my dish. I've got my feed. And some of it is missing the edge of the door. So what I'm trying to do is make something out here. So here's where I put my chicken wire.
But if you put them that way, I've seen them where they're, it's like, almost like they're at right angle to that.
Anything will work. This blocks more. You can almost do it like this.
As long as the feed
Do it like
doesn't
this,
take ground.
as long as it's not seeing dirt.
Dirt is bad.
So why not? I guess at some point, I'm trying with the optimal side of it, is what I'm trying to do. I mean, you don't wanna put it at the bottom of the can, right? So only a couple, what, a foot maybe, or
Bigger is better. What you get is most of your feeds are going to have a pattern like this. For transmit, you want the signal here and the signal here to be about -10 dB. For your ratio, this gives you most gain out of the dish. For receive purposes, you want this to be about -12. Your trade-off is, this is using the inner side of the dish, and it really isn't using the edges. And this is why most dishes have about a 50%
Efficiency.
efficiency. Now, if I take this, make up my feed, turn my feed at an angle and give it a lot more gain, and only use this part of the dish, and then cut this away. I've just invented the offset feed dish, which you see for all the direct TVs. They're only using part of a much smaller dish. And now I've got a beam going out like this. I've gotten the support structure out of the beam. I don't have to worry about the preamp seeing itself. But good luck figuring out where you're pointed when you put your own feed on it. That's one of the big headaches with this.
well, I repurposed, just the dish, just the temperature and stuff. And so it's offset, and 100%, that was the bane of our existence, is figuring how to aim.
Ah, this is what they like to do in England. Instead of having it like this, you turn it 90 degrees. Now the uncertainty is in your antenna rotating.
I mean, I tried everything, I had the goniometer, and finally what I had to do is just by trial and error, just set my, voltage control oscillator on there, and aim it at the sun, and just trying to figure out, and I had to get it so, okay. When I think it's right, then I put an actual carpenter square on it to get it to put the goniometer, so I had to actually figure out just trial and error.
We've done this on the antenna range many, many times. We'll set up a little aluminum tube or a cheap rifle scope or something on that and give the guys an opportunity to line them up. It is an uncertainty with an offset fed ditch.
But back to this, so you're saying, literally, if I put this at the bottom of the can, so make them, long, that's better?
Well, you're now making a 10-foot diameter horn antenna.
Yeah.
It would certainly have very good noise temperature.
But am I not missing part of the signal here? I mean, I'm cutting off.
Well, your
Well,
signals
well,
should all be
You've got
coming.
10 times the metal in this as you have in this. By the time you finish, might want to just make the dish a foot bigger in your head.
Can I draw a picture?
Have you seen the SETI dish antenna?
It just gives the NPV ratio is 0.45. And I just go super high because.
Oh, there's a magnet hiding in there.
The SETI dish antennas have this big tongue down here at the bottom to try to keep the ground reflection out of the dish.
And that, yeah, and that's right, they're using that like pie shape, it's like a 3D pie shape on the bottom of it there, yeah, that, I remember that.
Any other questions?
I have something I wanted you to comment. Let's let Steve finish. Okay. I wanted you to comment on the, one time I was trying to build an antenna and I was trying to get a whole bunch of gain out of it, but I wanted a bunch of bandwidth, and I'm talking to Ken about it. He says, you've got 3 things you can do with an antenna. And what are those 3 things? You remember? You got the bandwidth.
You got your
Okay.
choice. You can have gain, small size, or bandwidth. Pick 2.
Gain, small size. So you got physical size of the antenna, and you got the gain, and you got the bandwidth. So you have to pick what you want out of that combination. So if you want a bunch of gain, like you're saying, make a great big antenna, you know? But so therefore you, like Nathan was saying, you got a certain amount of space and a certain amount of money. What are you gonna spend and what are you gonna do with it? All right, that's one point I wanted to bring back that I thought was real good for me. I want you to, if you would, Kent, just describe your antenna range to them so that when they go home, if they wanted to try to do their own antenna testing, and we have one gentleman that is doing that, trying to do that,
Yeah.
and asking me questions about it in the background.
There's a comment on engineering projects. I want a good response. I want it quick. I want it cheap. Pick 2. I want it good and cheap. It ain't gonna be quick. Same thing with antennas. I want lots of gain, small size, bandwidth. Pick 2.
Okay, talk about an antenna range.
I have an antenna range that I have hauled to about 25 or 30 different conferences. We find a place in the parking lot, set it up. Guys bring in antennas and we test them for them. This gives them an opportunity to actually optimize them, find out where they work or don't work. You find some unusual ones. What frequencies do they work on? So we test all kinds of stuff. Usually we end up testing between 100 and 125 antennas at the conference.
Not sufficient for walking.
We draw the bottom line at about 50 megahertz. Have no problem going anywhere from there up to 30 gigahertz, and I'm spotty up to 60 gigahertz. So we test a lot of different ones. So here's our test area. I set up a horn antenna on the ground. It's actually sitting on the ground. It's now, it makes the ground plane part of my antenna. And I end up with a nice pattern like this. We come back here, somewhere around 100 feet, give or take. I take another horn like that, move it up and down, and I find an area where the signal varies less than a dB. Mark it, and then that's what we test. And by setting this up just right, I can usually find some place where it's about head high, so don't have to make it ridiculous. The signals here, we have a signal generator, and it's modulated from 1,000 hertz AM. Makes a nice tone. I come back here off my antenna, and we run a large number of designs. Have a diode detector. That comes down to an AC voltmeter with a dB scale with 1,000 hertz audio filter in it. That's how I receive it. So the receiver doesn't even care what frequency it's on, as long as the diode still picks it up. Then I learned the hard way. Come off here, have an audio amplifier and a speaker, so I can actually listen to it. We had I am not a fan of helix antennas, okay? I've had far too many of them on the antenna range. The Krauss's equations for the helix antenna are 3 to 4 dB optimistic. assuming you build it right, which almost nobody does. I had one that was being made for a satellite. And it had really weird responses, and then I finally figured out that the helix was tuned to TV channel 4 as a quarter wave width. And I was picking up a lot of video. So putting a filter on it helps. What happens? Here's a wire, and I'm gonna send a signal down it, and it travels at about 95% the speed of light, see, right? Just going down a wire. Now I'm gonna take, and I'm gonna have a slab of dielectric. I'm gonna put it in circuit board, and I'm gonna put the wire along. It now has a velocity factor. It's been slowed down, and that's on the order of about 60%. Give or take the dielectric constant here. So what the guys do when they make a helix is they run the equation, which is for a free space helix. Then they take a plastic piece of water pipe or something like that and wrap the helix around it. Well, the signal's going down that helix at 60% of what you think it's going down at. So all the turns ratio and everything else is messed up. I'm not gonna say you can't compensate for this, but I tell you what, go down to Ace Hardware and ask them what the dielectric constant of their PVC plastic pipe is. Oh, I'm smarter than that. I'm gonna look it up on the internet. Standard dielectric constant is measured at 1,000 hertz. Not 2,000 or 3,000 hertz. Can be done. I've never seen anybody actually do it.
Let me go back to the antenna range point. The one other piece that you've got that makes it more interesting, right now, what he's described to you, you could do relative measurements of the receiving antenna. But he has reference antennas where he knows what the gain of that antenna is. So he can put his antenna at that place and see what his signal is on the analog meter. And then he knows what the power level is, and he can measure your gain on the.
And that's where this one's calibration sticker is. I think I need to replace it.
So you have, to get that, you have to go to one of these antenna ranges that people are doing this and have reference antennas. But like the ones we saw this morning, it was a reference antenna. The data was available for that antenna at different frequencies.
I like using horn antennas for my references whenever possible, because the gain of a horn antenna can be calculated for this capture. And on this one, you notice I've got radar absorber on it. There's a tendency for the wave to come down here as a surface current and then wrap around the edge of the horn. That gets re-radiated out, becomes side lobes, messes things up. So I've got some radar absorber around the edges, and that breaks down those side lobes. Greatly
Is
reduces.
that material a ferrite of some kind, or?
It's, yes. Now, two places you can get it. You can get the silicon rubber loaded ferrite for about $120 a square foot from Mast or some of the others. However, the sheet magnets that you use for sticking a sign on the side of your pickup truck that says Acme Termite Company, that's not as good as the $100 stuff, but it ain't bad. So the sheet magnets actually work as a fairly decent radar absorber.
So Kent, let's wrap up and you can answer, he's gonna eat lunch with us, I think, and you can answer some more individual questions at that time.
Questions,
Maybe.
insults?
Go ahead and make your
Well, I do have a call, I mean, we can talk over lunch, but you know, when you used to be on top of. I really want to hear what Yes. Say. So I'm thinking of getting. Yeah, everybody's got a vision. Is there any reason why I shouldn't be able to be equally successful in that?
I would tend to look for the frequency you're doing. I would actually look for the older C-band satellite dishes. They're going to be in the 10 to 12 foot range if you can find any of those older ones. And quite often people will have one in the backyard that's been there for years. And if you're willing to haul it off,
Well, that's it.
mention a Cub Scout troop once or something helps a lot.
So just take that and apply the principles you talked about here.
Do we have any questions online? Do you guys have any questions?
Any questions from online?
You mentioned refrigerator magnets, had a 432 megahertz preamp that was oscillating, only when you put the cover on. And I put a piece of refrigerator,
Right, so you put the lid on it, didn't it?
yeah, so I put a piece of refrigerator magnet across the lid and held it on with a little glue, cured the problem.
And if
So
you
it
had
was-
measured the oscillation, you'd probably find it was oscillating up somewhere between 5 and 10 gigahertz.
Well, actually, I figured there was, several milliwatts coming out the input
Hey, Jason.
connector. And if you,
may
you
have a
remember the old
question
leacher
on that.
wire thing? You could-
Leacher wires,
Yeah,
oh my
well, you
God.
could do, what I did is I put a reflector on the bench and moved the reflector back, and I could see a repeating pattern. It was
It's called a tiny SA, they're cute little spectrum analyzers, sell for under 50
Yeah,
bucks.
but this was crude and effective, and I learned it was a,
And you've seen S11 game, haven't you?
Yeah,
Okay,
it's oscillating at 4 gigahertz,
Alan,
432 megahertz preamp. So that little piece of refrigerator magnet fixed it.
Okay, Kent, sit down. You're on. Bruce, you're on.
Oh,